Okay, supervised versus unsupervised learning. So I think I mentioned this a little bit in the nearest neighbors lecture, that essentially what we've been doing for most of the course is called supervised learning, which is given X, try to predict Y. But there's this other more vague thing called unsupervised learning that where we don't have a target that we're trying to predict, but we're just trying to do some stuff. And so today we're going to be in the same boat where we're not going to be doing supervised learning. So that doesn't mean we can't use the same data set. For example, in the nearest neighbors class, we looked at the housing data and we found the nearest neighbors of houses. So give me the 5 most similar houses to this query house using this data set. And we're going to do the same thing today with clustering. We're going to try to find groups of houses. So let me load this up. I'm not going to do a train test split. With unsupervised learning, maybe sometimes you still want to do a train test split, but it's not quite the same because we're not really going to be predicting anything and then going back and computing a score. So there could still be reasons to do a train test split, and I should really think more about what my recommendation is here. But in this case, I'm not going to bother. And then I'm going to actually make sale price, which used to be our target. I'm going to treat it as just another numeric feature here because I have all this information about houses. One piece of information I have is the sale price, but I'm not going to be trying to predict that here. It's just yet another piece of information, just like with nearest neighbors. Okay, so I'm just going to run all this code that you've seen a million times. And now we're going to start talking about clustering. So the goal of clustering, I know there's at least one person in the class who's interested in clustering because someone came to my office hours and was interested in this for their research. So we want to group our observations or examples together. So in this case, we have 1,400 houses, and we say we want to find a few groups of houses. Can we group together maybe 3 kind of groups of similar houses where houses in the same group or cluster are similar to each other and houses in different groups are different from each other? Not that this really helps you in any way, but in the future, I think I'm going to move this lecture to be right after the nearest neighbor one because they're very closely related in that they're both unsupervised and also they're both about distances. So we're going to be talking about how similar are they, how different are they. And so to kind of jog your memory, we talked about distances when we talked about nearest neighbors because to find a neighbor, we had to have a distance. So there's several reasons why you might want to do clustering. And so you might just want to know, are there groups of similar houses? There's this Malcolm Gladwell spaghetti sauce talk that is kind of a good example of this. And so I'll just talk you through it in 2 or 3 minutes. So let's say that you're a spaghetti sauce company and you want to make a sauce. And you have some kind of features of a sauce. Let's say how much tomato, how much salt, how much sugar, how much onion or whatever. And so each spaghetti sauce could be a vector. Let's say it's a vector of 5 numbers of those 5 ingredients. And then what you could do is you could say, well, every person has a different perfect spaghetti sauce for them. So if I bring in 1,000 people and do some taste analysis on them, I can get the dream perfect spaghetti sauce for each of those 1,000 people. And now I'm going to have a data set with 1,000 rows because I had 1,000 people and 5 columns. And each row is going to be the recipe for the perfect sauce for that person. And maybe I should. I mean, yeah, I'm not going to do it right now, but have. I'll do a very simple version. Tomato percent, water percent, person. So Mike likes this, and I don't know, Al likes this, and so on. So you're going to get yourself a data set, just like the data sets. Each row is a person, and you have some number of features or columns with the ingredients. And Now what we want to do is we can't sell each person their perfect spaghetti sauce because we cannot make a different spaghetti sauce for every single person in the world. We need to print labels for our sauce. We need to have our factory all set up to make our sauce and distribute them and set a price for each one and make a font for each one. So we cannot have a million spaghetti sauces, but there's some number of sauces we could produce, maybe 5. Maybe we can make 5 different sauces. So in that case, what I would like to do is I'd like to make 5 different sauces to make all my people out there as happy as possible. So can I find 5 sauces to make everyone reasonably happy? Meaning, everyone can pick one of the 5 sauces and have it be similar to their favorite. So in other words, I'm going to try and take all these 1,000 people that I brought into my taste testing, and I want to cluster them, to group them into 5 groups. The garlicky people, the oniony people, the chunky people, and I think what Malcolm Gladwell talks about is like the chunky sauce and the smooth sauce or something like that. And if I can find like 5 groups of people that in the group they're all similar, these people all like garlicky sauce, I can produce a sauce for those people. And now I'll produce my 5 sauces and everyone will pick the one that is their favorite, meaning they will pick the sauce that is closest to their optimal sauce. And that's how I'm going to make my customers as happy as possible. So that's an example where clustering might actually be useful. Any questions about that? Okay. So people often confuse classification and clustering. I'm just loading up some toy data sets here. So just to not confuse classification and clustering. So classification is you have some features and you have a label. In this case, there's 3 categories, and you want to, given the feature, predict the label. What we're doing here is we have features, but we don't have any kind of label, and we're trying to find groups. And maybe we're going to find here's a group together on the left, and here's a group together on the right, or something like that. But we're not given any labels to learn from in our training data. All we get to see is the features, and we need to figure things out for ourselves. So I've noticed these are really commonly confused, classification versus clustering. And as you'll see when we call that predict in scikit-learn, it gives you a similar output. So we need to be careful to not confuse these things. How would data collection work for this? I imagine not many people know the composition of what their favorite tomato sauce would be. Yeah, so you would have to figure that out somehow. But often, so that one might be a little difficult. You might have to give them a bunch of different tests and try to figure that out. For something like the houses, you already kind of have the data. You just collect the usual data, and then you just say, I want to find groups of houses. But yeah, I don't know what kind of taste test you'd have to do to people to figure out what their perfect sauce would be. But I think it might be possible if you give them, do you like this better or that better? And then just do that over and over again for that. There's probably a way. Any other questions? I guess I'll just say when it comes to humans, it's often you give them 2 options and ask them which one they like better and do that over and over again. It tends to be more reliable with humans if they only have 2 choices. Okay, so the first algorithm we're going to talk about is k-means clustering as a method of doing this clustering. And so we want to kind of find groups in a data. This is a 2-feature data set. Like in the very beginning of the course, why I picked the cilantro data set to start off the course is because there's 2 features and I could plot it and color things in. And it's the same thing here. It's nice to be able to look at it. So I'm picking some 2-feature data set, but I'll show it to you on the housing data as well, which is more realistic, but we won't be able to make all the nice pictures. So with k-means clustering, the number of clusters is a hyperparameter, which means you have to tell it in advance find me 3 clusters. And for the spaghetti sauce, that's fine. I mean, if you're willing to manufacture 5 sauces, then you're just going to set it to 5. But for the housing, we don't really know how many distinct groups of houses there are, and there's not really a good way for us to find out. So that's something we're going to talk about today. Yes. So the algorithm for k-means clustering, actually, I don't really want to talk about it. Yeah, let's just keep going. Okay, so in scikit-learn, it's k-means. So I imported this thing, and it has a fit and a predict. So it's easy to confuse with a supervised learning object in scikit-learn. But notice that when you call fit, you're only passing in one thing, one data frame with a bunch of rows and a bunch of columns, because there's no y value to pass in that we're trying to predict. So only pass in one argument because this is okay. So then when we call predict, well, let's run it. So we call fit, we call predict, and here's what it did. And I'm going to go through this in more detail in a second, but here's what it did. It took this 2-dimensional data set we had, and it found 8 clusters because that's actually the default. If we, yeah, so you can see right off the bat, the default for number of clusters is 8. So it found us 8 clusters, and then I plotted it with the coloring. And so it found this cluster, 1, 2, 3, 4, 5, 6, 7, 8. And the colors are completely arbitrary. It's just using different colors so we can look at it, but there's no meaning to the colors whatsoever. So it found 8 clusters, and you can see this is going to be a pain to come up with a score for this because we don't have like the Y train to compare with here. And that everything's just a little more fuzzy with unsupervised learning. So next I'm going to talk about exactly what predict is returning and such. Are there any questions though? Any questions? Okay. So here, for example, I can change this hyperparameter number of clusters to 3, and then this is the output. So that's a hyperparameter. You can set that to whatever you want. And there's some issues of like randomness, which is that when I rerun this, it'll give us, roughly speaking, or maybe exactly the same clustering every time, but the colors will change. So here we have green, purple, yellow. Now we have yellow, purple, green, and yeah, green, yellow, purple. So the colors are kind of being chosen randomly and different every time and arbitrarily. And as we'll see in a second, the colors are just integer labels that it's assigning, like 0, 1, 2. But if you don't want to deal with that being different every time you run the code, we can use our friend random state, and then it's just going to be the same every time. I was wondering if k-means is using the distance between points. Sorry if I missed that. Yeah, so I decided to just completely skip the algorithm part of it. That's in 340. That's also in a bunch of stat classes. I just thought it might be kind of not that interesting, / some of you have seen it before. But yes, it's using the distances between points. And so there's a cluster. Well, let me hold on for that for a second, and then I'll elaborate. The clusters themselves are deterministic. So yeah, that's a bit. So the like classic k-means and like the textbook k-means is it uses a random initialization or an arbitrary initialization. The scikit-learn k-means by default uses this thing called k-means ++, which I guess it still has some randomness in it, but less. but then it also has 10 initializations by default, which means it's actually doing the clustering 10 times without telling you and picking its favorite. And because of that, it's more stable. So I think if you don't set random state, the actual clustering itself could also vary every time, but it's not going to vary that much. Okay, yeah, so let me dive into this and then I'll get back to the question about the distances. So what exactly is happening here? So fit does two things. It assigns each point to a cluster. That's, in other words, coloring, giving each point a color. And under the hood, that's an integer. So if there's three clusters, there's 0, 1, 2. So if you want to look, this is the output. So the first point was in cluster 1. Well, all these are in cluster 1, cluster 0, cluster 2, cluster 0, cluster 2, etc. So it is assigning each example. So for the sauce, it'd be each person. For the housing, it'd be each house, to a integer label, 0, 1, 2, 3, etc. And those are getting turned into colors in the plots. The different numbers are different colors. And it's doing another thing. It's actually finding a cluster center. So for each of the three clusters, it's giving me a point in two-dimensional space that says, here's the middle of that cluster. And I can actually plot that as well. And here's that with these red stars. So fit is actually doing two things. It's assigning each point to a cluster, and it's giving us like a middle point to each cluster. So now going back to the earlier question about distances, yes, it's actually, what it's doing is it's computing distances between the points and these cluster centers, and that's why it needs a distance. So the way it decides which cluster a point is in is it takes this point here and it computes the distances. It says, how far are you from this cluster? How far are you from this cluster? How far are you from that cluster? And it assigns it to the closest one. It does that for all the points. Each point gets assigned to a cluster. Then it updates the locations of these centers by taking the average of all the points of that color, and it keeps repeating those steps until it stops. But I'm not too worried about those details for the purposes of this course, except that you should know that, yes, it is needing to take distances between things. So the central point for each cluster is literally the average of the points. So it's average of the x values, average of the y values. Is there a way to map clustering in terms of similarity between specific features if we know some feature similarities are more important? Yeah, that's a very interesting point. So this goes back to scaling. So we talked about scaling our features many, many times in this course, and we talked about how scaling is important for distances and nearest neighbors and all that kind of stuff. So generally you'll typically want to scale with something like standard scalar before doing this. But if you don't do it, then features with bigger scales will tend to take over, just like they did for distances and neighbors. If you have time, can you please compare and contrast the use of k-means and KNN? Yeah, so this is super commonly confused among students. So let me add something here. Okay, so k-means is a clustering algorithm, unsupervised learning. The input is your data frame, output is assigning each point to a cluster. So then nearest neighbors takes in a point and finds the k closest points. So that's what k nearest neighbors did in scikit-learn. But then there's also, I don't remember if I'm getting these names exactly right, but there's also these supervised learning. They use the nearest neighbors to predict a label. So why people get confused here is there's the unsupervised learning stuff and the supervised learning stuff. So today we talked about this. In the nearest neighbors lecture, for 90% of the time, we talked about this. Given a point, find me the closest points. which is very similar to k-means, except that k-means is labeling every single point in your training set as a cluster. But then we very briefly last time talked about the supervised learning equivalent of these, where the way you did supervised learning is you took a point, find the ones that were close to it, averaged their target values to give you a prediction for the target value. And these are quite different because these are for supervised learning, so they're addressing a different task. Question is, wait, so the central point is like a pre-existing point in the data set? It's not. So it's not this in k-means that these centroids or cluster centers are not pre-existing points in the data set. They're just some point in the two-dimensional space. And so if you did this on the housing data, you would get a cluster center for cluster number 1 in the housing data, and it would be some fictional house because it would be like a feature vector for houses. And it wouldn't be one in the original data set. And it would be like, this is a kind of representative house for this house cluster, or this point is like, here's the middle or the representative point for this cluster. And when you call fit, it does the clustering, but it also picks these cluster centers. Okay, yeah, I'm not going to, so there's a question about the algorithm. I'm going to run out of time if I go into the algorithm, so I'm just going to leave that for now. If you're interested in the algorithm, I would recommend checking out the 340 video. There's videos for all the 340 lectures available on YouTube. I put them there, so I would check out the one for clustering, and it will go into full detail on the algorithm. But I don't want to run out of time by going into that. So both KNN versus k-means use nearest neighbors in a sense to achieve different goals based on the presence absence of labeled data. Yeah, I would agree with that. I would rather say they use distances. K-means doesn't exactly use nearest. I mean, it's not necessarily about what is the nearest neighbor. It's just about how close is this, how far is that. But yes, they both use distances to achieve different tasks. Any other questions? How can you visualize this when there are more than 2 features? Well, you can't. That's the thing. You can only look at 2 features at a time. There are ways of attempting to do this under the umbrella of dimensionality reduction. Yes, so PCA is one of those things. We don't cover those in this course, though. How can we be confident if the clustering is reliable? Any scores? We'll talk about that in a second. What is the output of k-means? Like, how do we name the clusters? Yeah, great point. There is no way of naming the clusters. So once I do the sauce thing, I have to go look at the 5 sauces that it found, and I have to come up for the name with them by looking at the features. So, hey, this one has really high in garlic. I'm going to call this the garlicky sauce. This one has higher tomato chunk diameter. I'm going to call this the chunky one. You have to come up with that yourself. And so same for the housing one, and I'll show you that in a second. We would have to come up with names like this is the old house cluster or something. But it's hard. It's hard. Okay, question. Could there be a deployment phase for clustering? So kind of. You can, once you're done the clustering, you can take a new example here and assign it to a cluster by checking which is the closest cluster center. So if I have a point over here, where's my pen? If I have a new point over here, I'm going to say, yeah, I'm going to assign it to this cluster because that's the closest point. And so if I have a new person, I can find the closest sauce and say, hey, you're going to buy that sauce. But not all clustering methods can do that so easily. So the answer is sort of, I guess, depending on the particular algorithm. But you can definitely run k-means.predict on something that's not in the training set, like 0, 0. Come on. I'm going to do that to me. Oh, whoops. np.0. Sorry, I wasn't paying attention. Yeah. Okay. So this is the 0.00, and it's going to predict that this one's in cluster number 2. So there's kind of a deployment phase. Okay, so let me, but what if the number of deployment data would make a population that could actually be its own cluster? Excellent question. But the thing is, sometimes you have to stop and commit. Like, you can only do 6 months of market research. Then you got to make your sauce. The factories are running. They're in the stores. You've printed the labels, put them in the jars. After that, you're not going to change your sauce anymore. So if you have a new person, all you can really do is say, hey, new person, I think this is the sauce you're going to like best out of the 5, which is basically calling predict on that new person. But for some other applications, it's not too late. And if you get new data, you'd rather just reclustering everything all over again. So it depends on the domain. Is there an algorithm for which K is not a hyperparameter? Yes, we'll get to that. But first, I want to apply this to the housing data. So here's the housing data. I've run all the pre-processing, so you can see scale, 1 hot encoding, all that kind of stuff. In this case, I'm going to run k-means on it with 3 clusters. And now I have clusters for all my houses. Apparently, this first house is in cluster 1. The second house is in cluster 0. And what I can do is I can add that as a column to this data frame. So I added at the very end here. You can see I've added cluster as a new column. That is like cluster according to k-means. So now each house is assigned to a cluster. And again, I don't know what to name those clusters yet, but we can try. So we can look at them. So for example, now I can take all the ones that were predicted in to be in cluster 0. And I'm just printing out a few kind of important features that we've been paying closer attention to over the last few weeks. So cluster 0, cluster 1, cluster 2, and so we can, and I'm just computing the mean. Sorry, that's falling off the edge. So apparently the houses that were assigned to cluster 0 seem to be a lot older than the houses that were assigned to cluster 1 or 2. Now remember, the clustering was based on all the features, all 300 features. So, but I can't draw anything in 300 dimensions. So I'm just kind of doing my best at trying to understand what it was doing. But this does seem to be kind of older, cheaper houses in lower quality in cluster 0. And then these 2 clusters look kind of similar. Maybe the houses are a bit older in this one, but they may be different in other features that I'm not even printing out here, or they may be different in their combinations of features, because remember, there's distance. So it might be that one of these is kind of way over here and one of these is way over here. Or it could be that they're kind of spread out in ways that it's hard for me to understand. But I could try to name these clusters, and I could look into them more detail. Maybe I would call this the bigger house cluster and this the smaller, newer house cluster or something. And yeah, I could try to make plots. Like I can just plot 2 features here, year, built, and sale price, and color it by the cluster. But I can't really see much of what's going on. I wonder why it's grayscale. That's kind of annoying because I can't really tell the difference. I can't see the white ones at all. I'll have to fix that. Yeah, and also keep in mind that I performed the clustering in the encoded space, meaning after 1 hot encoding, because I was just using Euclidean distance, so it needed to be already a numeric data type. I couldn't use the categories. And so all that clustering took place in this 300 dimensional space, but the original housing data frame only had 80 features. Questions about this? And while you think of questions, I'm going to scroll up in the chat. Okay, we talked about that. We will talk about scores very soon. Okay. Yeah, okay. I think we caught up with all the questions. Is there something similar to SHAP for clustering? Oof, good question. I don't know. I really don't know. Can you post that question on Piazza so I can look into it later? I think that's a good point. I don't know the answer. Alrighties, well, it's 11:35, so why don't we take our break here? But I promise after the break, we'll talk about scores. We'll talk about an algorithm where you don't have to set the number of clusters in advance. So stay tuned for those, and I'll see you back at 11:40. It's surprisingly hard to get reasonable colors here. I don't know if you can really see the yellow, but it's better than white. But yeah, it's kind of interesting. I mean, we can see the clustering, like there's clearly this thing down here for low sale price and low year built. That's kind of the older, cheaper houses. But the blue and the yellow clusters, like we can't tell apart super well just by looking at sale price and year built. And presumably, like it's different features that are pulling those apart and making them separate from each other, or the combinations of features, but we just can't really tell by plotting it because we can only plot 2 features at a time. So there you have it. Yeah, we're not behind schedule. I think we're okay. In case anyone cares, I think, so last year I had all the true or false questions in class, and I think what happens is that on Zoom, people are less shy, which is awesome. And then there's a lot more questions, which I am happy about. And then there's no time for the true false questions, which I'm pretty much okay with. So that's that. Choosing K. Okay, so yes, scores. How do we decide what is a good clustering or a bad clustering? So can we have some sort of score for the clustering? So for K-means, there's something called inertia, or the sum of the intra-cluster distances, which is popular. So basically, like for every point, how close is it to its cluster center, or something like that. So would we want this to be small or large? We would want this to be small, in the sense that if we had these really tight clusters where everything was really close to each other, so we had a bunch of close things over here, a bunch of close things over here, that's like a very clean clustering. If there's a lot of blur and overlap between them, then that's more of a like a messy, nebulous clustering. So there's a bunch of words here, but let's look at the picture and then get back to the words. Okay, so here's what I'm doing here. I'm varying K. Remember, K is the number of clusters. So I'm taking that 2-dimensional data set and doing 1 cluster, 2 clusters, 3 clusters, 4 clusters, 5 clusters. And in each case, I'm computing this inertia thing, which, by the way, is supplied by scikit-learn. So if you go down to attributes, you'll see that after you call fit, you can get this inertia thing, sum of squared distances of samples to their closest cluster centers. That's what we talked about. Get me out of here, please. Okay. Okay, so that's this inertia thing. And what you basically see is that the more clusters you have, the lower this value is. And that makes sense because the more clusters you have, I'm going to have to scroll up, even though I don't really want to. Sorry. The more clusters you have, so if I make 20 clusters here, then every point is going to be very close to its cluster center because I just have so many clusters. I mean, if I make 1 cluster per point, the distance will be 0 because every point will have its own cluster, and then its cluster center will be right on top of that 1 point, and the distance from itself to itself will be 0. So definitely, the more clusters I have, the smaller this inertia value is going to get. But that doesn't just mean use giant amounts of clusters. And so that's kind of the problem, is unlike, so in supervised learning, this is like our training error, basically. And if we flip this around, it's kind of like our training score. As we make the model more complex, which is moving to the right here, the training score just gets better and better and better and better, and that's what we're happening here. But we don't as much have like a validation, a cross-validation score that's going to get better and better and better and then start getting worse again, and we'll have this like peak and we'll be like, oh, that's a good cross-validation score. It's not too simple, not too complex. That's not so easily done here. And so one method that you could use is literally visual inspection. So some people call this the elbow because it kind of looks like an elbow shape. Here's the hand and the arm and the elbow. So some people call this the elbow method, and basically say, well, as I make more clusters, things get better every time, but they get better not that much better after like 3 clusters. So there's this kind of corner, this elbow at 3. So I guess I'll just go with 3 clusters. It's very like incredibly subjective approach to picking number of clusters, but it is much harder to have an objective approach here than we did when we had something like cross-validation score in supervised learning. Let me just take a look at the chat. What happens if more clusters than points? That's just not really like a scenario of interest, I guess. Is this similar to the idea of super deep trees? Yes, in the sense that I'm talking about increasing complexity, but there's no trees here. Okay. Could you briefly explain again why we choose the elbow point? Sure. So as we add more clusters, this inertia score thing is going to keep getting better because points will be closer packed within their cluster. But it seems like, for example, going from 1 to 2 or even from 2 to 3 clusters, there's like this very big benefit that the score gets way better. But when we go from, say, 3 to 4 clusters or 4 to 5, it only gets a little bit better. So it's like, why should we bother adding that extra cluster to only make the score a little bit better? That seems not worth it. Maybe this is really just 3 distinct groups. Because if it was really 3 distinct groups and you set it to 3, you could always chop one of those groups in half and make it 4, but that's not really what you want. And so what we're saying is, well, if we add another group and the score only gets a little better, that probably means there wasn't like a 4th group all by itself, because then it would be way better if we set k to 4. And so that's the intuition for picking the elbow. Are we able to think of the clusters as a 2-dimensional space, or is it multi-dimensional? Well, that's the problem. It is definitely multi-dimensional. It is however many features you have, that's the dimensionality. So if you're doing this clustering of text messages like you did in homework 6 and you're using those spacey word embeddings, those were 300 dimensional and you would cluster in 300 dimensions. Actually, weirdly, this housing data is also 300 dimensions, but that's just pure coincidence. But here, 2-dimensional is nice for drawing, but it's not a realistic scenario. That's not what your problem is going to be, most likely. Okay, so I'm going to do the same thing for the housing data. I can get this plot, and like it's pretty unclear. I don't even know what to say about this. Like, I can't really look at this and tell you I should use 5 clusters. I think this is kind of telling me there's just like a smear of data for the houses, and there aren't really like super obvious distinct groups of houses. And yeah, you might just pick k depending on what you're trying to do. Okay, so another method for getting a score or choosing k is called the silhouette method. And here's how it works. For each point, it's assigned to a particular cluster, but you also find like the second best cluster. If this house or point wasn't going to be in this cluster, what's the second best? So in this plot here, this is just another toy data set. Here there's kind of 3 super obvious clusters. And if you want to take the green point is in this cluster in the lower left. But what is the second best cluster that this green point could have been in? Well, we look at the distances of the green point to the points in the same cluster. So that's these black lines. And then we look at the distances from the green point to the blue cluster. That's these blue lines. We look at the distances from the green point to the points in the red cluster. That's the red lines. And then we look at the averages. So if the average distance to the blue cluster is less than the average distance to the red cluster, then we say the blue cluster is kind of the second best. And that gives you a score for that green point. So it's like the distance to the blue points. Okay, yes, the actual definition is a ratio. It looks at the distance to its own cluster and the distances to the neighboring cluster. And in the silhouette score, okay, so someone's asking, why is this helpful? Well, basically, if a point is really, really close to points in its own cluster and really, really far from points in other clusters, that means the clusters are well separated. That means like there's clearly something over here and something way over there and something way over there. Compare that with a situation like this, where they're not well separated. They're kind of smeared together. So if I took a point and took a distance to its buddies in its own cluster versus the distance to another cluster, they wouldn't be that different. And so that would be like a worse situation where all the clusters are on top of each other and they're not clearly separated. Because what we want the score to tell us is like a good score is we have a bunch of clusters that are far away from each other, and a bad score is everything's just smeared on top of each other. And so that's why we're computing these distances. So if I go back down, we have the silhouette score that's comparing your distances to your own cluster versus distance to your other cluster. And you get a score for each example, not just for the entire situation. So actually in SHAP, we don't even need to go there. Anyways, you have a score for each example individually, and you can make these really crazy looking plots, which I will show you. Sorry, I don't want you to be looking at this. I just want you to be looking at that. So you can make these crazy looking plots called silhouette plots. I took the code to make these plots, adapted them from the scikit-learn documentation. So what you're seeing here is like, here's the toy data set. You say, well, what if you set k equals 2? Then you have these two clusters. Now each row here, where's my pen? It's like a bar chart, a horizontal bar chart. So what these lines are is they are the silhouette scores for each point in that first cluster. And typically you would sort to them from highest to lowest score. And so you get this kind of silhouette shape, which says for this cluster number 1, and remember the higher scores are better over here. So for this cluster 1, you have like a bunch of points with really high scores, but maybe it's hard to see here. You have like a couple points with lower scores, and those points are kind of unhappy. That might be these ones over here. And then for cluster number 0, which is this one over here, again, each row here, each horizontal line is 1 point, one training example. And the silhouette score is on the x-axis, so it's like a turned sideways bar chart. And then you're sorting them by the score. So you can see this one has like some happy points with a high score and some unhappy points with a low score. And the kind of shape of the curve tells you this drop off of like how many points in this cluster are not that happy about being in this cluster. And maybe that's these points over here that are like kind of close to their own cluster, but also kind of close to the other cluster. That's probably these points down here with a lower score. Questions about this plot? How does the second best relate to this plot? Okay, right. So each of these silhouette scores, so each horizontal line here is the silhouette score for a single example in the training data. And the way that silhouette score was computed was a ratio of distances from that point to its own cluster versus its second best cluster. That's how each individual score got computed. And now I keep getting this flipped in my head. So bigger score is better. So it must be the ratio of the neighboring cluster to your own cluster, because then bigger would be better. You would want higher distance to the neighboring cluster, lower distance to yourself. What does a bad silhouette graph look like? Yeah, so we'll talk about that in a second. So what I took from the scikit-learn docs is I can make this plot for different values of k. So when k equals 3, you see this. And when k equals 4, you see this. And I guess you could say maybe this is a bad silhouette plot. Like, for example, for this cluster here, there's this very fast drop off. So there's a lot of points in this cluster that are not really happy to be there. They have a low silhouette score. And indeed, that cluster is kind of stuck between two other clusters and maybe shouldn't be its own cluster. Maybe that should all be one big cluster. So things that are more kind of rectangular and far to the right are kind of happy looking clusters. And these clusters that have this sharp drop off with a lot of points with very low silhouette scores, those are kind of unhappier looking clusters. What does the red dotted line represent? Yeah, I think it's the average score of all the points, if I remember correctly. How did we know which is the second best cluster? Is it based on the center point, or do we compute the distance with each cluster and compare? Good question. The silhouette score does not rely on the notion of the center point, which is useful because it means it can be used on clustering algorithms that don't even have the notion of a center point. We're about to talk about one. And so to get the distance, it actually takes the average distance to all the points in that second best cluster. And that's what that plot was showing. Here. So it's taking the distance, the average distance to all the points in another cluster. It's not using the cluster center. It doesn't rely on the existence of a cluster center. How can the silhouette plot be interpreted to choose k? Yeah, so again, this is all super subjective. Like, it is hard to choose. I mean, you can maybe look, there's a bunch of eyeballing here. It's way, way more subjective than the supervised learning stuff we did. But you might look at this and say, I don't know, this cluster doesn't look good to me. You know, this, gotta clear my drawings. This looks healthier to me. But it's extremely subjective. And you can also plot the silhouette score. Sorry, for like averaged over all the points, changing k. So now this is the average silhouette score, average over all points, and you could try to do an elbow thing here as well, but it's again very subjective. Okay, so I need to stay on time here, so I'm going to keep going, but I can do the same kind of thing with the housing data set. I can make all these plots. So you can already see the housing data set is less well separated than that toy data set, in that these things are falling off very sharply. And they actually get to negative scores at some point pretty quickly. So, I mean, choosing k is a separate thing, but in general, the housing data set appears to be much more of a blob and not like a bunch of groups of houses completely separated from each other like the other data set. In terms of the scores going negative, I forget the exact formula that makes it go negative, but the interpretation is kind of similar to the R² score we saw in regression, that it's like usually between 0 and 1, but if things are really crappy, then they can be negative. Okay, I'm going to keep going because of time, so I'll just keep going. All I'll say about this section is this quote: specifying an appropriate dissimilarity measure is far more important in obtaining success with clustering than the choice of clustering algorithm. So it's really important to think about your distance metric. Do you want to use Euclidean distance? Do you want to use something else? Are you going to be scaling when you're using Euclidean distance? And well, I guess it's kind of embarrassing to put up this quote and then say I'm not going to spend any more time on picking the distance metric, but that's where we're at right now. I should try to think if I can come up with more resources for this. But for a lot of the data we're using, if you scale and then use Euclidean distance, it'll be okay. Or you can use cosine similarity like we used before as well. But for other types of data, you might come up with other types of distances, and we did talk about that a little bit before. So one question is, for the housing data, like, did we need to transform everything to numeric? Well, I mean, if we want to use Euclidean distance, yes, but if we came up with some custom distance function that could tell us the similarity between these different categories, we could just directly use that. But that would be more work in this particular case. Okay, yeah, so I'm gonna go past this for the moment. Well, I'll just say very quickly. Some clustering algorithms require the actual X vectors, meaning like the data frame. Some of them only require the distances. Like, you don't need the actual points, you just need the distances. I think I may have mentioned this in the nearest neighbor lecture, but I just wanted to bring this up because I have come across real world problems where you don't actually have the points, you only have the distances between them. And it's good to know that there are clustering algorithms that can work with that. So just keep that in mind. And other than that, I want to keep going. Because what I want to do is introduce you to another clustering algorithm. Someone asked earlier, what if we don't want to pick K in advance? So DBSCAN is a clustering algorithm implemented in scikit-learn that does not require you to pick K in advance. So here's some plots for which it is, well, in this one in particular in the middle, k-means is really going to struggle with this. K-means cannot really handle this because it's all about what's close to what. And so it'll try to make a cluster center here for the middle cluster, but the cluster center for the outer kind of cluster would be in the same spot. And so k-means could not really have the ring being one cluster and the inner ring being another cluster, whereas DBSCAN, which we're about to talk about, could handle that. On the other hand, both algorithms could do fine on this thing on the left because that's a pretty easy case. And the thing on the right, it kind of depends on the hyperparameters. So yeah, it's hard to tell how many clusters there are, that's for sure. I mean, this one on the left seems like 4 clusters. This one on the right, and the middle, I mean, I guess you could say it's 2 clusters, the inner ring and the outer ring, but it's all a little funky. So the way DBSCAN works is it uses this idea of density. Instead of saying there's like a cluster center and you look at what's close to it, you say that to be part of a cluster, there must be a certain density of points. It must be like X points per square inch. It's not really inch, but like per unit feature or per volume in feature space. And so the hyperparameters here are how many points do you need to call something a cluster? Because remember, we're no longer saying how many clusters we want. So we'll just say you need a minimum 5 points to be called a cluster. Here's how far apart points can be to still be together. And you can specify a distance metric. And you can see all that in scikit-learn DBSCAN. So epsilon is this distance, min samples is the number of points to make a cluster, and this is the distance, and there's some other stuff in there as well. And so let me show you some pictures because I think that'll be more useful than talking. So here's an example of a data set which is tough for k-means. So if I call k-means on this data set with k equals 2, then my intention with this is to say, well, this is a kind of banana cluster, banana-shaped cluster, and this is kind of a banana-shaped cluster. But k-means cannot really deal with that because it just has the center point, and it's kind of like putting a sphere around each center point. And it doesn't look at the connectivity, whereas DBSCAN is exactly looking at neighbors and saying, hey, you're close to me, come join my cluster. Oh, you're close to that person, come join my cluster. Whereas k-means just says, hey, I have a center point, everything near me is in my cluster. Hey, I have a center point, everything near me is in my cluster. And so we should be able to do better on this kind of shape of data with DBSCAN. So with k-means, I could increase the number of clusters to 10, but I mean, that's not going to solve my problem. This is not a good clustering. Whereas with DBSCAN, I can get kind of the clustering we want. So this is a scikit-learn thing. Again, it's the same kind of fit. Oh, question in the chat. How did you bring up the documentation like that? Seems very useful. Yeah, I should have mentioned that a long time ago. In Jupyter, if you do Shift-Tab, it brings up the documentation. And it's actually very useful because you can do something like np.sum, Shift-Tab, so any function or class or whatever. And I should have been doing that the whole time so I didn't have to keep scrolling all over the place in my notebook, but I forgot about it. Yeah, so here with DBSCAN, there's no .predict function, so it's different. So with k-means, we had this idea of like a test point where we had like a new point after we called fit, and then we said, hey, which cluster is this test point in? Which sauce does this new person prefer? We called predict, and it put them in somewhere. With DBSCAN, it's kind of like all in one shot. So you give it your data set, it'll assign a label to each one. I'm accessing the labels like this, but because there's no cluster center, there's not really a notion of like .predict. Which is fine. For most of the time you're doing clustering, you're not really going to need to like deal with test examples anyway. But it's good to know that k-means has that option and DBSCAN doesn't really. Another thing that's different about DBSCAN is this. With k-means, every point must be assigned to a cluster. With DBSCAN, you're allowed to leave some points unassigned. It's basically saying, I got to be within this distance of 0.3, but this point is not really close to any other point, so I'm just going to leave it unassigned. And if you look at the actual values, scikit-learn uses the code of -1 to say, I'm not going to assign that point to any cluster. So you shouldn't interpret -1 as its own cluster called -1, because you might have one over here and one over here, and those two are not in the same cluster as each other. They're super far away from each other. They're just unassigned. Okay. Is DBSCAN more robust to outliers? In a sense that it will just ignore them and leave them unassigned, whereas with k-means, an outlier will have to be part of a cluster and it will shift that entire cluster, which you might not want. So I'm happy with that, sure. And so I can run DBSCAN with different hyperparameters. Again, critical to mention, the hyperparameter is this distance. It's saying how far do points have to be in their own cluster. So when I reduced this distance from 0.3 to 0.1, then I only got these smaller clusters because there's a smaller distance. And even these points over here are not close enough to the yellow to be considered part of the cluster. And furthermore, there's not enough of a density of these points over here to make a new cluster. So there's tons of unassigned clusters here. But when you have a sufficient density of points as determined by the min samples, so in this case, if you have at least 5 points that close to each other, it gets to be a cluster, then you make a cluster. And so this number of clusters equals 14 was not inputted in at the beginning. I only inputted this EPS hyperparameter. And it just came back to me and said, hey, I found 14 clusters. So to answer that question from half an hour ago, or however long, this is a clustering algorithm where you don't have to decide in advance how many clusters, but you still have to decide something in advance. So it's not exactly like going to solve all your problems. So yeah, you can mess around with these hyperparameters and see what happens. And I should say that I am completely aware that I'm rushing again, and I don't like it when I have to rush, but I want to get through everything. So I'll just keep going. Okay, so yeah, this banana thing was an example where DBSCAN works better than k-means. Here's another toy data set where k-means works a little better. And the reason for that is because, remember, DBSCAN is based on density. So in fact, the D stands for density. So with k-means, for this data set with k equals 3, everything's fine. You just get cluster 1, cluster 2, and cluster 3. But DBSCAN gets super confused by this data set because as you set the hyperparameters, oh, whoops, sorry. This is the blank slate with the, this is the k-means, so it does well. And when you try to run DBSCAN on it, it gets kind of confused because either it merges these two together, and I say, okay, I have to reduce the distance then, so it keeps these separate. But if I reduce the distance, then this part on the right isn't like dense enough to become a cluster. So either the ones on the left get glued together, or the one on the right is like not dense enough to be a cluster. And so this is maybe the best you can do here. But it can get kind of tripped up if some clusters are way denser than others in terms of how the spacing of the points. So I guess this isn't that terrible actually with setting this to 2. Yeah, so the inertia thing for scoring that we talked about earlier works for k-means because it has a center, so you can compute the distance to the center. With DBSCAN, we don't really have the notion of a center, but you can still use the silhouette method, which is why I said earlier, the silhouette method doesn't rely on having a center, and the benefit of that is you can still use the silhouette. So you can say, here's my silhouette for k-means, and maybe I decide to have this many clusters based on the plot, and then I can do it for DBSCAN as well and kind of compare them. But this case, I'm not varying the number of clusters here, I'm varying this hyperparameter because with DBSCAN, I cannot directly vary the number of clusters. Okay, that was very rushed, I know, sorry about that. I want to talk about hierarchical clustering, so I'm going to jam this into the last 8 minutes. So the idea with hierarchical clustering is maybe you don't just have a cluster over here and a cluster over there, but you have this like big blob of pretty similar things, but then within it you have like some subclusters. So for example, maybe this is a big blob and this is a big blob, and then within the big blob on the left you have these two subclusters, so you have this kind of hierarchy of similarity, and that's exactly what this is going to do. And so a nice data set for this is some United Nations votes. So for each country, it has votes of different countries on different UN resolutions. And you basically get this data set of countries and a bunch of features which come from these different UN resolutions. And now it's just a regular looking data set with 17 rows, 17 countries, 368 features based on these UN resolutions. And we can try to cluster the countries. We can say, hey, which countries are similar to each other? And we could completely, totally just use k-means or DBSCAN here, and that would be fine. And we have these types of countries and these types of countries. But you could say to yourself, well, the situation is a bit more nuanced than that. I mean, there's not truly like fixed group of countries. Diplomacy is more fluid than that. And so maybe we can build this hierarchy of similarity to learn more about the differences between the countries. And so let me go straight to the punchline here. I think that'll be better. And we can go back to this if we want. But Essentially what we're doing is we're computing the distances between countries. I'll say this. And what we're going to do in this hierarchical clustering is we're going to find the smallest distance, which in this case is between Italy and Portugal. So of all the pairs of countries, the smallest distance between them in this particular feature space of UN resolution votes is between Italy and Portugal. And so what we're going to do is merge Italy and Portugal into a cluster together because they are the closest together. And after we do that, we're going to have a new kind of row and column that is Italy, Portugal together. So Italy and Portugal have been merged. And so for the next iteration of this algorithm, we're going to find the distance between, you know, Austria and Colombia, and the distance between Japan and this emerging cluster of Italy and Portugal. So Italy and Portugal got merged together. And now you need a method of finding the distance, not just between one example and another, but between a cluster and another, because this is now a cluster. And there's a few ways of doing this. How do you find the distance between Italy / Portugal and Japan? Well, you could take the closer of the two or the farther of the two or the average of the two, and those are all valid. In this case, I took the closer of the two. So you do that, you sort the distances again, and you find, okay, the next closest thing is the Netherlands with the Italy-Portugal cluster. So now you merge those two together. And so now you have Italy, Portugal together, and then Netherlands is like the next thing being merged onto them. And if you do that all the way to the top, you get this plot called a dendrogram that looks kind of like this. So this is kind of the punchline of what I'm trying to say with hierarchical clustering, is that instead of just getting a fixed cluster of these countries are together, these countries are together, and that's it, you get this richer information. So and it's very similar to like an ancestry plot, if you've seen those kind of things in biology. So these got merged together first. They're kind of the most similar. And then Netherlands, and here's kind of a cluster, and here's kind of a cluster. So Denmark, Norway are kind of together, and Austria, Spain are kind of together. But there's like this mega cluster of all these countries that are actually all kind of together. And you know, the Malaysia and Sri Lanka are kind of similar, but actually there's, you know, this bigger block over here. And in this particular data set, in this particular analysis, the US comes last. So the US is kind of considered like on its own. Yeah, and not really similar to other countries. But okay, I breezed through the algorithm too fast, but the output of hierarchical clustering is worth focusing on, in that you get this kind of richer output. And you could threshold this. You could say, okay, I'm just chopping things off right here. And in that case, you know, these all got clustered together, or something like that. But often it's actually informative to see the entire dendrogram, which is the name of this plot. Questions about this? Okay, so in Python, scikit-learn doesn't implement hierarchical clustering as far as I know. So you have to leave scikit-learn. SciPy, which you all have installed in your environments, it's a dependency of scikit-learn anyway, so you definitely have it installed. SciPy package has these functions that I used above, and these are kind of the key functions. I guess as far as this course is concerned, I would like you to be aware that hierarchical clustering exists, but you don't need to be familiar with the syntax or anything like that. But you have these notes to refer back to if you ever want to do this. The height of the graph shows how close they are together. Yeah, exactly, that's right. So the y-axis is distance. So when this whole cluster got merged with this whole cluster, that merge happened right here at this like higher distance of 0.28, whereas these got merged together at this very low distance, so they're closer together. That's exactly right. And if you fiddle with the hyperparameters of this, you'll get different clustering. So don't take this as gospel as usual, but it's definitely useful. Okay, we don't really need any of that. Okay, we're done. So we covered a lot of material today. That ends the kind of coding heavy portion of the course. Starting on Thursday, we'll get into the communication for machine learning part of the course. Please do fill out the poll if you have a chance, just so we can see how everyone's doing. And I will get homework 8 out to you later today. So see you Thursday.